Hello, I'm Paul. I can barely see your laptop. Your privacy screen works too well, Matt.
Sorry.
So, the typical disclaimer, I'm not speaking on behalf of my current employer. Matt isn't either. And we're definitely not making any announcements or talking about specific product features or vulnerabilities. So, let's start by talking about what we're not talking about. We are not going to be addressing virtual machine security here. We're not going to be talking about runtime security here. We're not talking about securing laptops and desktops. Those are out of scope and honestly very, very hard relative to even the problem we're trying to solve here, which assumes there are guards at the door to the data center. We're also not talking about the TCG and TPMs and so on. And I know you are all here because of the Supermicro thing, but we're not talking about defending against hardware implants or vendors who are doing bad things. So this, we are talking about allowing customers to run on the bare metal. That, as you will see, is a metal bear on a cloud. So the particular thing that we're concerned about in this context is the firmware on the devices the customer can actually access. In a VM context, everything is abstracted away. They can't get to the low level. But we want to secure things and give people direct access to the hardware. So, again, the firmware we're concerned about. If you look at a modern server in the cloud today, it will have between 50 and 100 different places that have mutable firmware or writable data that might be accessible to an attacker. Individual chips scattered throughout the platform. We know that customers can run the firmware update utilities. The manufacturers give them to them. And it's hard to just turn that capability off when you don't need it and turn it back on because it's all wired directly into the hardware. If customers do that, and very often fleet management utilities, the automated tooling that they run in their data center will change to a version of a firmware on hardware that they trust. They say, oh, we only qualified this old version. We know our workload works with that. So let's just put it back to that while we're using this hardware. This is a great flexibility, very, very good for being flexible for the customer. Lets them do what they want with the hardware. But then when we get it back, we need to make sure that it is not malicious. We need to make sure that they haven't stuck an old buggy version of the firmware in the hardware. And we need to do this consistently and reliably. When you rent a system, we let you do what you want, but when we get it back, we need to be able to restore it to a pristine state, and it has to be automatable. This has to you have to be able to do this at scale, and it has to work every time. Update routines that depend on the firmware itself doing a good job of updating it fail more often than you think they would, unfortunately. And the other thing that we need is we need to be able to say, even if this device had a bug in it, and maybe we've discovered and fixed it, we still need to be able to assert that the version we're giving to the next customer not only doesn't have that bug, but that bug hasn't been exploited to backdoor the next customer. So I'll let Matt talk to you about the background.
All right, so as Paul was mentioning, there's a lot of things if you look at a modern server platform, even a laptop, but servers are just more of the same. So there's a lot of things in there. How does it get built? How does it end up? It obviously doesn't appear fully formed in a data center ready for us to use and rent to customers, right? The manufacturing line, the process that gets it there is actually pretty long and complicated and intricate, and I don't know if anybody's ever had to actually try and build a real physical server. It's a lot more painful than you could imagine if you're used to dealing with software. So not a whole lot if you're familiar with the old PCI architecture diagrams of like, what does this computer look like, right? Things haven't actually changed that much over the last 20 years. The I/O buses have gotten faster. We've taken some things that used to be discrete parts and put them onto the same package. But we've still got memory controllers, application processors, I/O devices, some management stuff, storage. The general layout, the general architecture, the way these components interact hasn't actually changed a lot, even though the protocols may be a little different now. One of the things that has changed, though, is that literally everything has a microcontroller in it, right? It used to be all hardware, pre-programmed functionality, hardware state machines. That's kind of gone by the wayside. Everything uses microcontrollers, and they all have firmware of some kind. So like up on this picture, I think the blue ones are the microcontrollers and the orange ones are firmware. So you've got, even for the DRAM, you've got some bit of data there that tells you how big this DIMM is and what the timings for it are, right? Because if you want the system to support 100 different DIMMs from different manufacturers with different settings and sizes, you need something to tell the system what those are so it knows how to set up the memory. This gives the system a lot of flexibility. It allows you to build things. It allows you to fix things after you've built them. It allows you to plug different things together, and hopefully they all work because they can sort of tell each other what they are and sync appropriately. But it now also means we have a bunch of things to deal with, right? There's a whole lot more places things can go wrong, and we've now got a lot of people who are not software developers writing software to run in places that are not like easily visible or accessible or verifiable. And it's really like this is still the simplified picture. It's worse. There's more stuff in there, right? Most modern high-performance devices are no longer single core. They have multiple cores. They might have multiple different firmware images running on them. Your eMMC storage for your embedded controller probably has its own firmware in it. You've got other things on the board that may not be documented that clearly have some kind of non-volatile storage on them. Sometimes it's as simple as some part identifiers so that when you need to return something to the manufacturer, they can identify which part this was and send you an appropriate replacement. Sometimes there's actual like microcontrollers in your battery keeping it from exploding. So there's a lot of things, right? Your hard drives all have them. Your USB Wi-Fi device probably has separate microcontrollers on both the USB side and the Wi-Fi side. There's a lot of things in there. So there's a lot of places if you want to persistently store malware, there's a whole bunch of places you can stick it, right? And the ability of the system to go investigate what's in the hard drive firmware is generally pretty limited, because if you look at the protocol specifications for like a SATA hard drive, it doesn't have a command in there that says, hey, tell me exactly what your firmware is. It's got like an update routine that if you go look at the Linux utility says very clearly, don't do this, you'll brick your hard drive. So not only can people not inspect it, but they've been told explicitly not to even try updating the firmware on a bunch of these devices because it's dangerous. And it can be if the manufacturer has done a bad job building the device, but that also means you're not getting security updates when there's problems with it. So that's what's in a server. How does it come to be a server? Like there's tens of thousands of different components in a server, right? Individual components from passives to small active components like muxes and other things to the big CPUs that we think of as being the actual part of the server that we're interested in. And they're built all around the world. South Korea and Taiwan, Israel build a lot of individual components, right? And these sort of get farmed out. These are, in most cases, commodity things. So when you say, I want to go build a server, I need 10,000 of this resistor to put on the motherboard, somebody in your supply chain organization goes out and orders 10,000 of those from wherever they could find them, either available or cheapest, and then they show up at the contract manufacturer, and the contract manufacturer uses them. And there may or may not be good tracking of those all along the way from the place that built them to the place that packaged them to your contract manufacturer. But even assuming you have that, right? We've got components coming from one set of manufacturers. We've got PCBs being built in entirely different places. There's plenty of places that have a lot of PCB manufacturing, but the components and the PCBs are not generally manufactured together, right? The components come from one vendor, the PCBs come from another vendor, and then they all go to a third place where they get assembled, right? And this is, the assembly is usually where we talk about contract manufacturers, where we get all the pieces in the same place and somebody solders them all together. And that's great, but if you don't have tracking on what comes into the contract manufacturer, you're not really going to have a good idea of what you're actually getting. Is that the thing you wanted? I know there was talk this morning about this part of the supply chain aspect where you've got a whole bunch of coming things in. I think it was Joe Fitz that made the comment of just replace a reel, right? Like at the contract manufacturer, they're just going to have buckets full of the specific components and instructions on where to solder them down on the PCBs. If you can inject new things into the supply chain at that point, this is sort of where he was talking about it happened, somewhere in the process of taking all the individual parts, putting them in the same place, and soldering them together. That's a really hard problem to solve, tracking all that. We didn't really attempt to solve that problem. We were worried more about just the firmware, because all of these places, all of these components, all of them that are programmable, at any point in this process, somebody could be putting hands on it, programming it, testing it. In fact, hopefully they are putting hands on it and programming it and testing it, make sure it works before they assemble everything and send it to you. And so there's going to be firmware on these devices, right? Everything that's programmable by the time it leaves the contract manufacturer is going to have some firmware on it, because hopefully they have done some level of testing. And if they haven't, then you get really upset with them and you go yell at them and make them do that because you want them to send you working devices. And then once you have them, they get shipped all over the world, right? So I know there's the stories about customs interdiction of devices and reprogramming of them because they have to cross 3 or 4 borders to get from point A to point B. Because, like, as you've seen from the slides, you know, probably every part in your server has been around the world 2 or 3 times by the point it lands in your data center. So there have been plenty of opportunities for people to touch them, test them, reprogram them, and, you know, do something that you might not actually have good record keeping of, and probably not good ways to verify before it gets to you and you're ready to start using and running that server with, you know, whatever's on it. So a big part of the problem we're trying to solve here is once the system arrives, it's in my data center, it's now in a secured physical location, how do we know what's really in there, right? There's been some testing. Obviously, that has verified that the system functions, or we would have rejected it and sent it back. But in most cases, the firmware on there is not going to be what we actually want. The process of building this server has taken, on a good cycle, 3 months. So whatever versions of firmware were installed on this thing to test it as it was getting built are almost certainly out of date by the time we get it and we want to run it. Some of them might still be okay, but the odds are that everything on there's out of date. Probably has known bugs that we want to fix and get rid of and remediate. And test and verify that, hey, we've got this thing in the data center. How do we know that before we hand it to the customer, we want to give everybody a pristine system with a known set of firmware on it? How do we verify that on the system when it's ready to deploy, when it's ready to use?
So before we go into the new thing we're talking about, what we did to solve this problem, I'm going to go through a few of the existing solutions to this that are in the wild today. So the first place you want to start is with signed firmware. This means that you have vendor signs the bits that they put into the device, and this should prevent unintended code from running if they have done everything perfectly and have no bugs. Most devices are moving to signed firmware. The majority of manufacturers care about this. It keeps customers from bricking their devices. So that's generally a good thing, and NIST really wants you to do that. This works best when one vendor controls the system end to end. The limitations, though, you have, all the signature is saying is these are the bits that I intended to put in. It doesn't say that there are no bugs. It doesn't say there are no backdoors, and it doesn't even say that that it can prevent unsigned code from running. It just says using the normal process, we try to run only signed code. The other problem we have is that runtime firmware could prevent the installation or the update of the new firmware you want to put in. This is a fairly common feature of the BIOS backdoors. When people have been developing those, they want to prevent you from taking their backdoor out. And so accepting an update and saying, great, I've applied that, and then dropping it on the floor is a pretty easy thing for a runtime firmware to do, and it's very hard to verify that that sort of thing hasn't happened. The next technique that people are using is what's called secure boot. This is definitely better. It generally consists of a ROM, a very small ROM that's masked into the device, which takes a checksum of the firmware that it's about to load and makes sure that it's signed by the vendor before it actually runs the firmware. This is great because it means that your code is checked at every boot. The downside is it doesn't give you any runtime protection, and it also still has the issue associated with configuration, which is expected to be changed at runtime by the customer. The vendor can't sign that because it doesn't know what the right values are there. And oftentimes we'll see exploits that are actually, the exploit is written into the configuration area and then exploits a parser that allows you to leverage code execution, even though the device is running signed code from the vendor. The other difficulty with this is it's very hard to end up with a functional revocation mechanism where if you have a downgrade vulnerability or the vendor has lost their keys, updating often requires actually just replacing the hardware. That's hard to do at scale, and it's very expensive. By the way, the configuration vulnerability that I discussed is how we got into the Intel ME last, what was that, about a year ago?
Yeah.
The most recent one. So the other thing that we have in devices is, or that we would like to have in devices, is a way to measure what firmware is running. This is rarer. We're working on making it more common, but usually this is a process where the device signs something using a private key stored in the device, gives you back that value, and when this is implemented correctly, it gives you assurance that the code that is running is the code that you intended to load. So TPMs are supposed to work this way. Google's Titan chip works this way. This is also limited, though. The biggest one is very few devices support it, and the measurements are often unstable. As firmware changes, as pieces of configuration change, you can't hash over the configuration for the same reason you can't sign it, and unless you're in a very, very carefully controlled environment. And even then, serial numbers and MAC addresses and so on mean that you don't necessarily have matching hashes. So this is hard to do at scale. It's easier if you have very, very similar hardware, but it's difficult to do effectively. So our challenge, signing is insufficient as currently implemented. Most devices don't give us measurement. And we need assurance about the running firmware. We need to know what is inside our device.
So as someone noticed from my water bottle here, I've not always done security. Before I did security, I did hardware engineering and validation. And one of the things about pre-production hardware, just like your first attempt to compile software, it doesn't ever actually work. The first version of something new is going to have a lot of bugs. Things that you expected to work right, even very simple things, very critical things are not going to work, right? And you're going to end up with either a very expensive doorstop that you thought was going to be a prototype you could use for development, or you're going to waste a lot of money building more prototypes as you fix every little bug. That gets cost and time prohibitive real quickly if you have to do new production cycles every time you need a bug fix as you're going through trying to bring up a new piece of hardware. As I mentioned earlier, manufacturing's hard and takes a long time. So hardware manufacturers do have capabilities to take something that is not working, right, that doesn't have good firmware on it, that has bugs in it, and still do something with it, right? The process of taking sand and turning it into a computer involves a lot of work and a lot of debug and a lot of validation. And the hardware engineering community has put a lot of effort into figuring out how to do that, how to determine, hey, does this transistor work? Hey, does this CPU work? Hey, does this laptop work? Without throwing it out and building a whole new thing. So, what happens is when you're doing firmware development, right? You've got a platform, hot off the presses. You've got this brand new thing in front of you. You're real excited. You want to boot it up, right? You just want to get BIOS to run through so you can get to an EFI prompt and test some things. You first get that, there's no firmware, right? You've maybe done something in an emulator that you have to put on here. Like the very first time, there's nothing on the system to even accept a firmware update, right? You can't run a capsule update before you've got the very first BIOS installed. The update routines are often not the first thing you develop, right? You're not worried about updating something if you can't even get it to power on and accept commands. Very often, when you're doing firmware development, you will make a mistake and the system will hang. And it's real hard if it hangs before you can get back in to update it to get your new code in to see if your bug fix works. Another big problem, even if you're doing signed firmware, if you have implemented that incorrectly, you now have a problem because now you can't update because your signature checking is broken in some way that prevents it from accepting an update. Very often hardware features don't work. If your non-volatile storage controller has some bugs, you may not be able to do writes. There may be protocol issues, there may be other problems that just prevent the system from working as intended. So if you're used to dealing with production hardware that mostly works, you're like, well, just run the update. And that is just not something that's possible on pre-production hardware. You can't rely on most of the normal functionality that you would use to do things because it is either not there, not implemented, or just not working properly. These have largely been solved, right? We are able to ship new systems. I think most of the people in this room can go out and buy a new computer or work on new systems. This obviously isn't blocking us from shipping things. This is not an unsolvable problem, right? And what's happened is most hardware, both components and higher level platforms that are components put together, have recovery mechanisms that allow the developers to continue running tests, to load new firmware into the device when it's not working. And these mechanisms don't depend on certain levels of functionality of the software, right? They're explicitly designed to require as little of the system to be in a functional state as possible. So things like JTAG is really designed to work with a very, very small number of transistors actually operating normally. And let you find the other ones that aren't, right? So if there's problems with the system, as long as your JTAG controller is working, you should be able to get in there and go start querying other parts, go put instructions in and make sure they're executing properly, and do things to the system in a way that it doesn't really matter what the state of the rest of the system is, right? It's designed to work regardless of what is currently happening on the system or what has happened in the past, because it was designed under the assumption that probably everything is still broken, right? And we need to go and be able to diagnose and figure out what's going on and then make it work again. Lots of systems have recovery mechanisms built into ROM, right? There's a real common implementation is you have a jumper on the system and you put a jumper on a header, and now it goes into some fail-safe mode that allows you to recover the system into a known state. Lots of systems have debug serial ports that are active all the time, no matter what the actual firmware is doing. And there's way too many other proprietary mechanisms to attempt to go into all of them. But everybody who's done this has had to come up with something to allow them to go back and recover the system when it's not working, because you can't brick all your prototypes if you want to ever ship product. So we asked ourselves, hey, there are mechanisms in the server we can use to force it into a known state. Our firmware developers are using them during the course of their day jobs. Can we leverage those for security too? I don't think anybody got the joke. This is the band Yes. Somebody suggested we like play the song there, and I'm like, I don't want to rely on audio working. Yeah, the answer is yes, right? We can use these recovery mechanisms to get very high assurance of the firmware on our platform, right? We can go in, apply the updates to like the runtime, the mutable firmware, without relying on any code that's actually running on the system. Right, and this gives us assurance because the mechanism we're using doesn't depend on the runtime code. It doesn't depend on what's currently on there that we don't know, right? If we assume that like very malicious things are on the platform, or it's just been completely erased and the thing is a brick and we can't run the normal update routines, like this gives us a mechanism to go in sort of regardless of where the system is now, hit it and bring it back to where we want it to be. And so this gives us assurance because it doesn't really matter where it is now. We believe the mechanism works regardless of what's currently on there. And when we're done using this mechanism and pushing the firmware we want into the system, we have very high confidence that when we start executing that firmware, that's going to be what's really running, because the mechanism we used to put it in was kind of oblivious to whatever else was going on at the time. And so there's lots of ways to do this. As I mentioned just a minute ago, options from booting the device into a specific recovery mode. JTAG often allows you to load known code onto a system and then start executing it regardless of what's there. Most of this ends up being somewhat specific to the device. The process is always a little different. But almost everything we've looked at has some mechanism to do this, because that's the thing the developers of the system have been using to do this. I just covered most of this. So, real common one is sort of the jumper thing, and the device will go into, it's usually called a recovery or an anti-brick mode. And very often it'll just sit there and wait for some custom undocumented vendor utility to supply it a new firmware image that it will then write to its storage. And then when you reboot, you come back up into a known state. And if you can convince yourself that that mechanism will actually, write the firmware you're giving it to the storage, regardless of what's on there, then when you can be confident when you reboot, that's what's actually there. Sometimes it's a multi-stage process, right? Sometimes you update just the bootloader and then you reboot into that and go do a normal update from the bootloader. Sometimes it's, you can use JTAG to force a known thing in there, or provide an image over a serial debug port that the runtime firmware doesn't actually have access to interfere with. The mechanisms vary a lot, like I say, and it's quite device specific. I thought this was in the next section. So how do we use this, right? We've got tens of thousands of servers in data centers. Putting jumpers on things is great when they're sitting on your desk. That doesn't work when you need to do it to 10,000 systems on a daily basis, potentially. So in order to operationalize this, we built custom hardware. We kind of had to. It gives us connectivity to whatever the interfaces on the specific components we're trying to require are. It has things like UART and JTAG and other interfaces that we can plug into different components. We intentionally tried to make it flexible enough to support lots of different devices from lots of different vendors. And it's actually just sort of a simple thing. And it gives us a path to go from our server management system to actually go, drive whatever interface on the specific device we need in order to put it into the recovery state. And because we're relying on this, right? This is now becoming the thing we trust in order to repave all the firmware on the rest of our server. We very explicit made it not runtime updatable. So if we need to reprogram it, we do have to put hands on to reprogram our recovery device. And that was a very intentional choice because that means that there is no mechanism from software running on the system to modify our recovery device. There's just no wires there. There's no connectivity. It can't be done because it's not connected that way. And that means that when we do use this, we've got very high assurance that we programmed it. It is what we expected. We've got the firmware running on our recovery device that we expect, and because we have physical possession of the systems and control over who has access to do that programming, we have pretty high assurance that it's actually working as intended.
Am I doing the show and tell? I thought you were.
Am I?
Oh,
I don't know.
I mean,
Okay.
I think you may have done one of my sections, but
Oh, yeah.
that's fine.
So yeah, as I was saying, we did build custom hardware. It's actually not interesting. It's not much more than an Arduino on a custom PCIe form factor card. It turns out if you want to stick something into a server and you need connectivity to something outside the server, you don't have a lot of options for what form factor that's going to be. There are PCIe edge fingers on there. The only thing hooked up is power. We draw power from the server, and that's it. Turns out we don't need to recover servers that don't have power. Doesn't help much. So it's like the form factor is kind of irrelevant. It's basically an Arduino on a custom PCB. And like I was saying, it's got connectivity to a bunch of things, so we can plug some wires in, make the operations people very unhappy about the extra wires, and use those to I see nodding in the back, very unhappy. And use those to, instead of having to walk up and physically place a jumper onto a header, we now have wires going to it that we can flip through a GPIO on this thing.
Do you have other questions at the end, or do you care?
Questions now is fine.
I'm curious, what did your operations people estimate the additional cost of building per server is for this?
It's not much.
I don't mean the cost of building the board, but the cost of time wiring it in.
Oh, the time wiring it in? I don't actually know that. I remember, the cost per board was trivial. It
did take a while to get the people who were wiring to do it correctly every time.
I'm kind of wondering, this doesn't really give you any rollback protection for
That's the point.
updates that go back to,
that is a feature, not a bug.
okay?
I don't know how many firmware updates you get from your vendors. I get a lot. Some of them don't work.
We build our own anyway.
Sure. How many of your internal firmware updates have critical errors?
They have loads of critical errors. There are ways to roll back to one previous version. There are no ways to roll back to previous versions of that.
So, I mean, we have in fact, sorry, I should be closer to the mic. So we have in fact, where I know this has worked and where this has saved a lot of time and money is we actually at one point did get a firmware update from a vendor to fix a bug that introduced a new bug that basically bricked a bunch of devices. And we were able to use this to roll back to the previous version on a bunch of devices that were otherwise inoperable and would not have been able to be rolled back automatically. So all the pain it caused to try and install and use this thing, everybody was real happy we had it when we started needing it.
I think
Sure.
so. Let's talk a little bit about the limitations, including what you mentioned. We had to build this custom. This is not something that we could, if we gave you one of ours, it wouldn't be very useful to you for your servers. The other thing is you really need to cooperate with the manufacturers that you're doing this to. You need information from your server vendor, or you're going to spend a lot of time reverse engineering stuff you may anyway, even if the vendors are being cooperative. Unfortunately, they often don't know how their device works either. But it's a bunch of work, especially if you're trying to do it without cooperation. The other issue is on many of these devices, the flash chip is used for debugging. It's used for runtime metrics, logging. And so when you have the data center reliability folks who come by and say, hey, we need to figure out why this thing failed, can we look at the last 100 hours of logs or whatever, you say, well, it went to a new customer and we blew that all away. Great. The previous customer can't backdoor the new customer with that data. Not so great. We don't have the data anymore. As you mentioned also, the cabling is really, really annoying for this because most devices are not designed with the idea that their debug ports are going to be wired up during production in the data center. As we move forward with this and we work closely with the vendors and we redesign our boards, the cabling gets better, but it's still not perfect. Cables falling out, headers that are pins rather than latching retention, all things that enterprise server people care very deeply about for reliability reasons. I already mentioned reverse engineering. The other thing about this is that it very often requires you to cycle power to the device to take up the new firmware you've installed. If you're in a shared environment, you have multi-tenant, something like that, that may not be tenable for you, depending on exactly which hardware you're taking this approach to. If you are choosing, say, a network card vendor, you've got to look and see who has this capability and how they've implemented it. Again, you need to sit down with the vendor and have some conversations that they don't usually answer correctly the first time around because it's hard to understand the question you're asking. So if your chosen vendor can't do this, then you may have a problem. You may have to switch vendors or ask them to build the feature for you. The other thing is for some devices, the flash chip is inexpensive and you only have 10,000 writes. If you do this all day, every day, eventually you're going to wear those out, and then your device stops working. So make sure that is something you've taken into account before you do it. The other thing is, part of the reason that we ended up doing this was because we knew that it was possible for someone else to do it. If we have this low-level, known to blow it all the way at the hardware level functionality, we don't need anti-rollback protections like you were mentioning, because we know that when we put it into the state, that's the state it's in, and it's not, it can't be backdoored then, not in terms of the firmware. It's not the bugs that were in the previous firmware can't keep it bricked.
It will only have the vendor supplied backdoors at that point.
Yeah, I'm giving everyone the same backdoors. Did you have a question before?
I actually was wondering if you only did this for your host CPU firmware, or did you actually do this for all the devices you listed earlier?
A great many of them. Yeah, it was.
So there's more custom hardware than is it just the PCIe card?
So the PCIe card was wired to all the other hardware.
Okay, so that's the vendor support.
Yeah, there's custom design more than just the PCIe card. This is what he was saying, that we could give you one of these and it would be useless if we don't give you the server to put it in also.
Yeah.
Okay. So talking about things going forward here. One of the things that we're working towards is figuring out how to do this in-band on the device. For some kinds of devices, this is already possible. But so going in over the PCI Express bus rather than having to squish firmware down over serial cables dangling around the inside of a server is definitely optimal. The other thing we'd like to move forward with is getting it to the point where you can do a full firmware reset on the devices without resetting the host. This has both the nice property of if you're using them for multi-tenant, you can still get them back into a known good state, but also means that the recovery can go much faster. One of the challenges of this is servers are very slow to reboot. If you have to do this a bunch of times, you end up with an hour or 2 hours. Our first unoptimized variant of it took a very, very long time. And if you have that in the data center, folks are going to be complaining about, we could be renting these servers. Why are they taking so long to recycle? So getting that time down, especially if you can do it online without a full power cycle, is a very ideal opportunity. The other thing that we are hoping we can move forward with is being able to detect if firmware has been modified. Right now, the best you can usually do is ask the device, hey, what's your version number of your firmware? It tells it to you, and then you either believe it or it was lying, and you can't tell that it was lying. There are some folks who have done some very clever things with looking at the timing it takes to do that, to try to figure out whether or not you're actually running what it says it is. But at the end of the day, it's an arms race that I don't think is practical to play. The better solution is ask the vendors to give us hardware-secured ways to figure out what the firmware is. And when we talked about this last time, I said that a vendor was working on this for us, but I couldn't tell you who. Now there is, Intel has actually published the draft spec of their hardware-level firmware attestation. And the way that works is they have a ROM in the device that does a checksum of the it does a hash. Yes, I won't say checksum. It does a hash of the firmware before it boots it, and then it puts that into a locked PCIe register so you can get that value out of the device. And because this all happens at the hardware level, you have very strong attestation of exactly what booted in that device. What you do with that value is up to you, but it allows you to see in a way that you couldn't before. So I strongly recommend taking a look at that and commenting on it with them. There are some things in there that are also solve other problems, but the bits about getting the hash of the firmware I think is very interesting. The other limitation, this doesn't do anything for runtime integrity. That's a very hard problem. We'd like to hear your ideas, but the fundamental issues are, until we have boot time integrity, trying to solve for runtime integrity is maybe not something that is worth the effort until we get this out of the way and we understand which firmware we're running on. But that's an area of a lot of research still. So conclusions here. Gaining assurance on your firmware is hard, but it is possible. Ask your vendors for these capabilities. The more we go to the people we're buying hardware from and say, I would like you to do these things for me so that I can secure your hardware in my data center, the more likely they are to do it. If we present a unified front to them in asking for these things, it's much more likely that we'll actually get change. And with that, we'll take questions.
How do you communicate to them?
Magic. It's got its own interface to the network. It's externally controlled, right? It's not something that comes in through the system. We issue commands to it from something else that gets plugged into the network by some other thing.
So essentially it's a specialized BMC.
It is like a BMC for a BMC in some ways, yes.
And it's much less complicated and much easier to do very careful audits on how it functions.
Several of orders of magnitude less code.
How do you know that you trust the new device that you put in there, not just the problem into a piece of hardware?
So as I said, it's small enough that in terms of the functionality in the code, that an individual can very carefully validate what it does. It is not updatable. One of the concerns we have is all enterprise hardware is built to be updatable in situ because that's how you deal with bugs in it. We really don't want that for this piece of hardware. So once we put the firmware in, because it's simple, because it's only doing a few things, I mean, it doesn't have the ability to, it doesn't have enough storage even to write out a backdoored firmware, and it's doing things like toggling GPIO pins.
Yeah, so that's being handled basically the same way. So on a whole bunch of devices, we have to rewrite all of the configuration settings when we do this.
Yeah, I mean, we have to do things like store the serial numbers and put them back in.
So, does that suggest that you are potentially carrying state across re-imaging for an attacker's MUD?
We store that data when we put the system into the data center, and we restore with known good values, not the ones supplied by the customer.
Known goods supplied by the manufacturer.
If the manufacturer is screwing with us, we have different set of problems than we're trying to solve.
Targeting back to 10 o'clock this morning.
Yeah.
Yeah. We're trying to ensure the vendor supplied backdoors and not the other customer supplied backdoors.
You?
So when you were talking about the scalability, the tool that uses Magic to connect, does it have to send one server at a time, or can you say, I have 50 servers that all should have the same firmware update, send all the 50 of them at once?
There's nothing that prevents us from doing that. It doesn't usually happen in practice because of just sort of the rate at which machines come back to be recycled.
The process, current processes involve, as Paul was mentioning, a lot of reboots. So we only do them when the systems are not being otherwise used. We have to move stuff around to vacate systems in order to run the process. So we don't generally have like 100 of these going all simultaneously.
And some of the limitations in terms of how long it takes are some of the processes, for instance, involve swishing firmware down over a fairly slow serial link. So that can only go as fast per machine as it can.
Yeah.
But there's nothing that prevents us from running it very parallel.
As far as I'm aware, there's no limit on how many of these we can do simultaneously, but the process is like, it's individualized, so you have to run through the set of steps on each server in the right order. It won't accomplish a whole lot, so you have to go through that on each server individually.
How many different I/O voltages do you have support?
I don't know that we needed anything but 3.3.
What was the question?
Honestly, how many different I/O voltages did we have to support?
We had at least one device that we were worried was going to have 1.8, but
I don't think we are
think it was
currently doing
taller.
anything that is other than 3.3 right now. But it ends up being a small number, right? Everything in the server is running generally on 12 volts, 3.3, or like 1.8, and there's not that many different like main voltages that you have to interface to.
So I'm curious, is this a device that you read your text and put into a server, or is this a device that you build into all of your servers and it's always on the network?
We build it into all the servers. It's always there.
Okay.
yeah, it wouldn't scale if we had to put it in every time you wanted a new server. I mean, we build clouds, right?
So did you say that this was it has a network device, so it has like a complete TCP stack and everything in this, or is it over like a simple serial link that is aggregated somewhere else?
One of those, yes.
The device itself is quite simple.
Yeah, that's what I was getting at.
I mean,
It has
at the end of the day, so at the end of the day, it does need to be connected to the network to automate it.
Right.
So we do have to control access to whatever is managing access to, right? Like, yes, we have,
Do you have anything else on that network segment, or
we do lots of other things
Yeah.
to control access to this to make sure that it is not misused.
Yeah.
if you've also pulled in TCP and like SSL and all that,
At-
to protect that?
At the end of the day, if the people walking up to the server want to do things to it, we have a different set of problems.
Okay.
So if you said it's a VMC for the VMC, then what is the VMC for your VMC?
You have to walk up to it to change
You have
the firmware.
Yeah, and we have actually, that process is somewhat involved.
Yeah.
So we do have some mechanisms for verifying that this has happened correctly and the device was programmed correctly, and we know that it hasn't been modified.
Yeah. There
So
are
there's-
some.
if you walk up and just try and touch it and do something not terribly clever, we will notice.
There are some bits involving crypto that they asked us not to talk about.
Do you do this at every reboot or only between customers?
Between customers. It takes long enough, you
So
don't.
if a customer kind of shoots themselves in the
We
Yeah,
you
I
can't
mean-
stop customers on bare metal from shooting themselves in the foot.
Yeah, I mean, and it's a feature too, right? You know, it is a very legitimate use case to say, I know that I have qualified this network card firmware for my software, and I don't want whatever the newest stuff is. Enterprise does that all the time, and customers want to do that, so we let them. Yeah?
So this approach relies essentially that your recovery flows in the firmware, they're not compromised, but in fact your recovery flows in the current modern firmware, they are quite complex. So how do you ensure that the original, the pristine version of the firmware doesn't have the backdoor, which will be basically your taking updates from your device and you're patching it and installing this on your spy flash or BMC?
So this is talking directly to the SPY flash, as directly as we can. So the original firmware may be backdoored. It may have a bug. It may have a bug that allows someone to get it into a, for example, about every year there are vulnerabilities in SMM that allow an attacker to write to the firmware, or write to the BIOS on a machine. Because we're not using the BIOS itself to do this kind of update, then even in the context of a world where we know there are either we found them or we haven't, but we know there are that kind of bugs, because we're writing directly to the SPY flash, we are bypassing the possibility of those exploiting the update.
Totally understood from the slide because I was thinking that you just trigger recovery flows from the current firmware and
No, we explicitly don't want to use the firmware's update routine. We're trying to use some hardware mechanism that does not depend on whatever the firmware is at this time.
Any other questions? All right. Thank you very much.